Kalau kamu nak programkan finite element tu, nak programkan finite element tu kan, pakai C program ke, MATLAB program ke yang kamu pernah belajar pada tahun 1 kan, ataupun whatever programming language, memang kamu kena supply this information, the element connectivity. Kalau tak, it's very hard untuk kamu solve finite element kalau tak ada element connectivity. Then this element connectivity will determine the angle of your elements. Okay, the angle of the element. Tapi kita dah tengok untuk plane trusses, its element connectivity, we show the directions of the elements connectivity from one point to another. But this element connectivity, it's actually will have a huge difference at the local stage sahaja. Sekiranya struktur yang sama, saya bagi struktur yang sama dikenakan elemen connectivity yang berlainan. So ada dua struktur yang exactly the same in term of dia punya geometri, material apa semua. Struktur A, elemen connectivity dia dalam arah yang lain. Struktur yang kedua, kita kenakan elemen connectivity dalam arah yang lain. Sebab the physical problem yang kita nak solve, kita tak nampak struktur tu. Kalau kamu tengok struktur bumbung kan, bumbung dekat stadium ke mana-mana, dekat train station ke, dia tak ada elemen connectivity dekat situ kan. So we engineer have to decide. So how we decide it? Okay, we decide kalau kita nak solve dalam finite element, before we solve the element stiffness matrix, then we have to tell the finite element tu macam mana satu elemen tu dia connected between each other, and then the arrangement of the nodal point as well. So we engineer have to decide. Alright, so that's for the a kind of structure which is under what we call it, axial deformation sahaja. So dia tak ada element of bending pun dalam within that structures. So kalau structure tu boleh digunakan untuk certain part of the building sebagai contoh, tapi if there is a huge loading apply or may exist to our structures or to our system, then the plane trusses itself, which is a kind of arrangement of a structure which is not, I think it cannot, dia macam tak sesuai lah untuk sustain the bending loading. So the most common structure that to support the bending, which is called beam. So that's why in many structures, components or system will have this beam. Sebagai contoh, if you look at the roof, so roof meskipun dia mungkin ada plane trusses, tapi dia mesti ada beam section juga, which is all the load that came from the plane trusses then will be transferred to this beam, because beam is usually very strong enough to support displacement and also bending. All right, let's look at this a bit of introductions. So it's mentioned here, beam is a structural element that primarily carries bending, which is in the form of flexures or transverse loading. So this is the keyword, bending here. And then beams generally carry vertical forces. Tapi jarang kita jumpa satu-satu structure tu it come with only beam, kan? Biasanya it came with a combination of beams which makes it a frame. Okay, bila dah jadi frame tu dia memang dah betul-betul kuat. Beam generally carry vertical forces, but they can also sustain horizontal loads. So meskipun dia carry vertical forces, tapi dia boleh sustain horizontal load. Sebagai contoh kat sini adalah earthquake. Ataupun kalau building tu, this is your building, maybe you have several beams to make your building. Kat dalam building tu dia ada banyak beams kan. So horizontal loads ni may came from the ground shaking, kan, ground shaking to the left, to the right, and then from the aerodynamic as well. So building tu dia expose kepada udara, dan udara ni dia bukan dalam satu arah aja. Hari ni pukul 1 arah sini angin, pukul 1 suku mungkin dah dalam arah lain. So benda ni pun influenced by the aerodynamics, not only the from the earthquake as well. So kat sini pun boleh letak lah, you can add here, which is this also may came from not only earthquake, but it may came from aerodynamics. Beams are characterized by shapes, cross section, the length, the material and type of support. So this is the characteristic of a beam. So there are several type of beams according to its shapes. Yang paling ketara adalah shapes lah, shapes. The length, material ni almost common, tapi shape is much more significant difference lah between one beams and the others. Beam are used in construction sectors, are typically made of steel, reinforced concrete or wood. So this is just very brief introduction to the beam. Okay, this is examples of the application of beams in building construction. So kita tengok we have some elements macam plain trusses dekat atas ni, but the biggest structures adalah beam. This is a beam, which is to carry the bending that transfers from this. Kita ada macam plain trusses ni kan kat atas. And then this figure on the right here, so the yellow one is the beam section. The beam section, which is the strongest part lah. Okay, and this sit at the stadiums. Okay, the seat structures ni, stage ni, so made of several beams structures. And then gambar yang ini dia lebih pada plain trusses ni actually, plain trusses. Because dia macam not very clear dekat sini where is the beam. I think mungkin ada somewhere tapi dia terlalu complicated, tak nampak dekat situ. Then beam is very famous in apa ni, civil constructions lah, civil construction. And then not only that, okay, in transportation vehicles, sebagai contoh, yang ni saya tambah sendiri ni slide ni. Sebelum ni tak ada, I think last 2-3 years I included this just to show the student that the beam is not only for the building, but it's everywhere actually. For example, this all the beams, which is for the ships construction. We use the beam here to carry the bendings and the vertical loading. And then this is to support the skin. Okay, tempat kita nak attach the skin. So kita ada banyak panel ni kan, panel-panel ni. So dia attach kepada beam. Actually dia bukan macam gini je. Ni this is the main lah, main. Actually dia ada yang small lagi tu. Alright, I have seen when I visited students conducting their internship dekat Labuan Shipyard. Okay, so bila pergi dekat sana tu, we have a group of students lah, rasanya 5-6 orang ke 7 orang at that time. Tu pun dah lama, I think 4-5 years back. So this group of students, they are very lucky because at that time, bila tahun when our country start apa ni hit by the apa ni currency drop apa semua ni kan, time tu lah masa minyak petrol apa ni the price of the crude oil dah jatuh tu, masa tu dia orang kat sana. Tapi at that time that company Labuan Shipyard, they still have to macam tugboats lah, tugboats yang besar juga. Actually dia panggil tugboats pun kapal-kapal yang nak tolak kapal-kapal kontena tu kan. Kan baru ni ada cerita berlaku dekat terusan Suez tu. Kapal kontena tu dekat terusan Suez tu dia tersasar sikit dan tersangkut dan menutup apa ni laluan kapal-kapal lain kan. So ada tugboats yang tolak benda tu. So this tugboat is very powerful. And this student, they very lucky. They have or get involved with the constructions of these two boats. Actually, Malaysia is very good actually in term of engineering. Cuma the design office kita tu kan, because design office tak ramai pun pakai staff. Dan kita design office tu yang kurang. Actually, the ship design came from Singapore, and then they construct it in Labuan Shipyard. So they can see the whole part of the ships. So for the aircraft, there are kalau you all ada dekat UTM, dekat Aero Lab dekat atas bukit tu, dia ada 2 biji aircraft kan, 3 biji. 2 fighter aircraft, Skyhawks, and then satu lagi tu transport military aircraft, Caribou. So kalau you all pergi dekat sana, you all boleh nampak dia punya structure aircraft tu, dekat mana beam, dekat mana stringers pakai. Then untuk aircraft, kalau kita tengok pada wing section, so dia ada biasanya kita ada 2 beams yang diguna pakai lah untuk support all the loadings that generated by the wing. Untuk aircraft, the most important components of the aircraft itu to make it flies adalah wing. Wing ni paling penting. Kalau tak ada dia punya badan dia ni pun still dia aircraft dan dia boleh terbang. Tapi untuk tujuan untuk carry passenger transportation, dia kena ada dia punya body lah, atau kita panggil dia fuselage kan. Then you can imagine how many passengers. So let's say kita ambil average, sekarang dulu 60 je average manusia, sekarang ni rasa dia dah naikkan rasa 65 ke 70 macam gitu. So let's say we take 65 darab how many, 150 lah let's say kita katakan. So this is the how many kilos lah dekat sini. And then your baggage lagi kan, your baggage. And then minyak lagi. And then berat kapal terbang tu sendiri. Semuanya tu actually bila terbang, semua tu ditanggung oleh wings. You can imagine how strong the wing. Very very strong kan. So the most safest part of the aircraft adalah around the wing area. Duduk dekat tail tu not very safe lagi sebenarnya. Tapi tail which is kat belakang ni, okay, this area actually is a very strong part. Sebab tu kalau kita tengok accident, aircraft accident, biasanya kalau dia putus pun dia putus dekat situ. Kan? Dia takkan putus sampai kat sini. Sebab kat sini there are so many spars there that makes that section very very strong. Dia banyak spar tu sebab dia ada connection dengan dia punya kita panggil dia rudders dengan horizontal stabilizers lah. So not only for the aircraft, for the car as well, you may find there are several beams. Dekat bawah pun ada, dekat floor, dekat dia punya roof dia, semua ada beam. So this is just to show you how important is the beam. Okay, yang ni I think you have learned in the solid mechanics. There are several type of beams that you may found in the market, which is in the type of I-beam, C-channels, hollow, angled beams. Kalau bentuk Z, sorry. It can be a beam as well, tapi biasanya untuk bentuk Z semacam gini ni, in aircraft kita panggil dia macam stringers, which is we use to support the skin, of the skin of the ni lah, of the wing ke skin of the fuselage. Alright, this is also improvement to the slide. Kalau dulu-dulu saya benda ni tak ada, but this is I put here the information of the moment of inertia, just to refresh you lah, to refresh all of you, that when we are talking about beams, then we have to consider its moment of inertia. So moment of inertia depend on how you look at the structure itself. Then you may have two moment of inertia, IIS, IYY. So yang ni pun saya tak nak discuss, tapi saya letak sini supaya bila kamu tengok benda ni, oh I have done this before during my solid mechanics ke apa kan. And then for different structures, shape of the structures, then you may have different equations to calculate the moment of inertia. So for the I section type of beam, so this is the equation. So if, for example, you are given the structure, the shape of the structures are known, then you may need to calculate the moment of inertia as well. Usually for a simple type of beam, which is maybe in the form of, let's say, rectangular or hollow rectangular section, Usually untuk ni lah, untuk rectangular or parallelogram type of beam, usually you need to remember this. Sorry. You need to remember IIS, IYY for the given structures. Then you need to know which one you have to use, IIX or IYY. But if, for example, a complicated type of structures or equations required to solve for the moment of inertia, then we will supply the equation. So in finite element, don't worry. We supply I think almost the equation. You do not need to remember everything, but you just need to understand where to use it, what it's for, and how to use it. Okay, now, before we go further, do you have any question, guys?
Saya,
Yeah.
kalau macam shaft tu dia dikira beam juga ke?
Shaft. Shaft tu tengok shaft biasa beam, dia ada bentuk dia tadi tu lah. Shaft biasanya dia bukan beam, tapi dia still boleh support apa ni, bending. Cuma kalau beam ni memang apa tu, its function untuk support the bending tu kan. Kalau kita ambil shaft biasa macam bar, kalau kita apply moment ke dekat dia, dia still boleh tahan juga sebenarnya, tapi dia not as superior as beam lah, macam gitu.
Alright, sir.
Yeah. Okay, very good questions. So yang lain tak ada soalan ke sama tidur? Kelas pagi ni kalau tak nampak muka macam ni kita tak tahu lah kan. Hopefully you all ada lah. Untuk BIM ni dia tak ada masuk dalam, dia biasanya masuk dalam test 2 lah nanti, dalam ujian 2 dengan final exam. BIM dalam ujian 2. Okay, dalam final exam dia tak ada BIM, tapi dia akan ada frame which is in the same topic tapi dia dekat belakang sikit. Alright, kalau tak ada salah saya proceed. Untuk BIM and solve using finite element method, the equation that we are going to solve later, which is still the same, which is in the form of K Q equal to F. Kan, ini macam saya bagi tahu awal-awal semester itu, kita akan jumpa equation ni almost sampai habis lah, system of linear equation. Cuma untuk heat transfer tu, system of linear equation dia bentuk sama, cuma dia punya variable dia kita pakai lain. Sebab kita dah consider untuk temperature kan, yang ni untuk force. So untuk general loading, because when we come up with structures, then we expect to use it in certain application, and this structures is to support certain type of loadings. Alright, for the beams, it says for our analysis, we consider 3 types of loading as illustrated. The first one is the distributed load. So, distributed loads ni, dia boleh jadi kita ada apa ni, kita ada macam beg pasir banyak kan. So, let's say kita letak loading tu, kita letak beg pasir banyak-banyak ni. So dia boleh jadi distributed load juga. Kalau kita ada this part of the this section of kita punya beam is attached to other structures that has certain weight. So dia boleh jadi distributed load ataupun under certain pressures lah, certain pressures. So we have distributed load. Okay, we understand the point load, which is the load that applies specifically at a known locations within our structures. And then we have concentrated moment as well, which is kita tahu exactly moment tu dikenakan dekat mana, dekat along this our structures. So we have distributed load, concentrated load in vertical direction, and also concentrated moments. So untuk beam, dia punya concentrated load dia adalah in vertical direction. Alright. So let's we look at the deformations of neutral axis. So saya baca dulu dan saya cuba explain. Due to applied load, so imagine our structure in its initial conditions, dia adalah yang mendata ni. Okay, yang mendata ni. So dia ini dalam keadaan dia punya rest. So when we apply load, then the beam may experience an in-plane XY deformation. So dia akan bend macam gini. So this is the one that we have with a solid black line ni, which is our beam yang merah ni, yang selepas kita kenakan load, so dia akan deform as shown here. Then it says here the deformation shape of the beam neutral axis is shown. So positive deformation is shown, which is represented by these notations lah kat sini. So at one point, okay, kalau kita, this is our beam. Kalau saya ambil any point along the beam here, then there will be two type of deformation. The first one is the vertical deformation. So daripada asal dia dekat sini, dia dah deform ke sana kan. So we have vertical deformation. And then daripada asal dia straight, sekarang ni dia dah deform to certain angles. So dia macam dah rotate. And then this rotation or moments at this particular point here is given by saya pakai merah V prime. So the positive deformation, positive deflection is positive in the upward direction. Then the rotation is positive in anti-clockwise direction. So this is the sign convention that we have to follow for solving the beams problem in finite elements. So beam dia boleh ada vertical deflection, displacement dan juga rotation ataupun slopes. Alright, elementary beam equation. So from the stress kita boleh dapatkan strain, and where M here is the I is the moment of inertia. So nanti kita akan tengok je ni. This is actually from the pure solid mechanics lah. Nanti kita akan tengok je ni nanti. Okay, now let's we look first on the discretizations of our beam elements, how we write the nodal points and elements numbering, and its associates rotation and also deformation at each nodal point. Alright, seperti yang kita pernah bincang sebelum ni, untuk for solving finite element model, for solving structural problems or any problem actually using finite elements method, first sekali kita kena ada apa, geometry ataupun physical geometry. This is physical geometry. Then from the geometry yang kita ada physical geometry, kita discretizekan dia. So kalau masih ingat lagi, kita kena discretizekan dia kepada elemen yang lebih kecil kan. Yang physical geometry ni mungkin kita ada beam yang bentuk dia yang I-beam ni kan. Tapi kita boleh modelkan dia dengan menggunakan finite elements seperti yang ditunjukkan dekat bawah ni. Tapi the informations of the cross-sectional area, the informations of the moment of inertia, kita transfer kepada setiap elemen tu. And then we discretize, then these two must be executed first. And then yang 2, 3, 4 ni kita boleh switch yang mana nak start dulu pun tak kisah. Let's say we look at the type of the material used. Material use, dia punya boundary conditions. And then the applied load. Applied load. So yang ni dia kita boleh switch lah which one yang kita nak start dulu, depend on the problem. Usually apa ni, kita boleh straight away tengok pada boundary condition dulu kan untuk kita eliminate betul kita punya rows and columns. Then after that, after we have this, we rearrange our equations in the form of system of the linear equation and solve for unknown degree of freedom. So in our case, our degrees of freedom in the form of deflection and also rotation. Rotations. So ini adalah untuk beam problem. Then from there, from the knowns deflection and rotation, then barulah kamu boleh solve for apa ni, for the stress, for the normal strain, for the normal stress as well, and then also for the reaction force. So pokok pangkal dia nak kena dapatkan sini dulu, deflection dengan rotation ni, baru kita boleh solve yang lain-lain. But how to discretize the geometry for the beam? Actually, to discretize the geometry for the beam sama dengan kita discretize bar problem. Satu batang bar tu, whatever physical shape dia, then kita discretizekan dia kepada beberapa elemen yang kecil. Usually untuk tujuan test exam kamu, biasanya kita akan limitkan lah the number of elements supaya kamu boleh solve problem ni secara manual. But actually this when kalau kita guna apa ni software finite element untuk solvekan kita punya problem, Actually dia tak ada limit, kamu nak solvekan dia berapa 10, 20 kan. Cuma apa tu, kamu dapat lebih banyak data, result mungkin lebih accurate sedikit. Dan ya, komputer yang buat jalankan tugas, so dia boleh buat kerja yang sama je. Sebab finite element ni kalau kita perasan, elemen 1, 2, 3, 4, 5, kalau kita ada 5 elemen ke 2 elemen, cara kerja dia sama je kan. Dapatkan K, eliminate rows and column according to boundary condition. So kalau elemen 2 pun sama juga. So dia adalah repetitive type of job. So we divide our structure into several elements, and at each nodes or nodal point, saya besarkan sini, at each node or nodal point, now we have 2 degrees of freedom as well, which is our degrees of freedom in the form of vertical displacement and also the rotation. So dalam slide ini, dia pakai Q to represent the deflections, vertical deflection, and also slope or rotation. But other than this, kamu boleh pakai instead of instead of Q, kamu boleh pakai U and V jugalah. U to represent vertical displacement, V to represent the rotation. Let's say saya pada node 1, pada node 1, dan kita ada vertical deflection at node pada node 1 dengan rotation pada node 1. So kalau nak pakai yang ni pun I think much more convenient sebab kita tahu benda ni U and V berlaku pada node 1. Kalau pakai 1, 2, 3, 4, 5, 6 pun boleh. Cuma kita kena set dalam kepala 1, 2 ni pada node 1, 3, 4 pada node 2 kan. Kalau saya recommend pakai yang ni lah. UV. Alright, at each nodal point, kita ada 2 degrees of freedom in the form of deflection and also the slope or rotation. So that means untuk satu elemen kita ada 4. Okay, untuk satu elemen kita ada 4 degrees of freedom, which is dalam positif sign convention dia adalah dalam arah sini. Untuk rotation adalah positif dalam arah lawan jam. Untuk deflection, the positive in the upward vertical direction. So yang ni kena faham lah yang ni. Dan dia kena sama, kita kena set dan kita kena guna positive sign convention untuk semua degrees of freedom pada setiap nodal point. Dia tak boleh bercampur. Kalau bercampur aduk nanti jawapan akhir kamu dah confuse. Ni sepatutnya deflection dia ke atas ke bawah kan. So that's why kita setkan the positive sign convention. Ada soalan setakat ni? So finite element senang je kan? Kalau dulu student takut tau finite element. Saya pun kenapa dia orang takut ni? So I try to make this finite elements much more easier lah kan. Hopefully you my explanations are very easy for you to understand as well. Okay. Someone comment tadi, jelas tadi katanya. Alright, thank you very much. Now let's relook at the Okay, now we come to the shape function. Kalau dalam beam, kalau dalam plane trusses, kita assume the deformation of our structure from one point to another is linear, kan? Linear. And then we apply N1 and N2. Ingat tak apa lagi N1, N2 ni? 1 minus Z over 2, 1 plus Z over 2. So Z apa? Z. Ingat tak? 2 over LE, X minus X1. All of this minus by 1. Okay, ini kalau kita assume dia linear. Tapi untuk beam, the deformation is no more linear. So linear assumption cannot be used in or to predict the deformations or behavior of beam structure. So to support this, then we use the Hermite shape functions. So apa tu Hermite shape function? So kita tengok kat sini. It says that we define a Hermite shape function so as to obtain the deformation at any point along a single beam element, and it is given in the form of H. So H is given by this equation, and dia punya I ni, the index I is given by 1, 2, 3, 4. Alright, okay, sebelum tu kita tengok dulu the next slides. Apa yang kita ada dekat sini? So this is our H. So kita ada equation untuk H tadi, which is dia ada constant A, B, C, D, and then kita ada Z. So our H is as a function of the term Z. Tapi Z dia adakah Z yang ni? Kan? Dan kita tahu untuk the value of Z, okay, the value of Z it still remain the same. Z on the left hand side is always -1 in our case, and Z on the right hand side is always a +1. Ini based on the textbook yang kita refer dan kita gunakan untuk kita punya ni lah lecture notes kita. Kalau kamu baca buku lain, then dia punya range of Z from one point to another mungkin dia pakai 0 hingga 1 pun boleh juga kan. Okay, next. Okay, then kita tak nak tahu, tak perlu tahu macam mana dia dapatkan H ni. But the H is given by this lah, by this H1, H2, H3, H4 is given by this equation, and it is as a function of Z. As a function of Z. Dan Z kita tahu on the left hand side of our element will be -1. On the right hand side of our element will be a +1. So untuk H1, dia punya mode dia adalah bentuk dia macam gini. Saya kecilkan pun boleh. Alright, this is the mode of the beams untuk Hermite shape function. Untuk H1, on the left hand side where Z equal to -1, then this -1 ni kalau kita transferkan dia punya value dalam H1 ni, kita ambil Z dia sebagai -1, then the value here will be kita dapat berapa kat sini? 1/4, 2 tolak 1, 1 1 tolak 1, 2, 2 kosong 2, 4. Then 4 darab 1, 1. Bagi dengan 4 kita dapat 1. So 1 which is on the right hand side. So on the right hand side, kalau kita tengok kat sini, kita punya Hermite-shaped function H1 pada position Z adalah -1. So dia displaced by 1 kat sini kan. So ini yang kita dapat tadi. Kalau pada position Z sama dengan 1, H1 adalah kosong. So dia duduk dekat bawah ni lah. And then daripada atas ni, then kita combinekan dia based on Hermite-shaped functions. Then kita akan dapat this kind of shapes that connecting between the left and the right side of our nodal points. Sorry, of our elements. Okay, itu adalah untuk H, which is refers to the Hermite-shaped function for the deflection. Dan untuk apa ni? Untuk rotation, then it is given by H prime here. So untuk H1 primes pada position Z -1, kita dapati dia punya rotation dia adalah kosong. Exactly at the node, dekat node ni, okay, dia punya H1 prime dia dah kosong. So maksudnya kita punya structure kita dekat sini ni, sebelum dia deform tu dia adalah perfectly horizontal lah. And then right after sikit je, dia dah start deform macam gitu kan. Dan pada nodes sebelah kanan, where our Z is +1, then there is no slope or gradient to the Hermite-shaped function or to our structures. Then we repeat the same process untuk H1, H2, H2, H3 dan H4. Dan kita boleh come out dengan this kind of tables lah. Tapi kita pakai ke tak ni nanti? Okay, nanti kita tengok. Kalau kita pakai, which part yang kita akan pakai. Tapi hopefully kamu boleh faham lah apa relation di antara the two slide on the left and on the right. Macam mana dia dapat H1, dapat equation macam gini. Yang tu tak apa. Kita tak perlu sampai that levels lah. Mungkin dia memerlukan some apa ni, some derivation. We need to know the value of A, B, C and D. The constant dalam kita punya H. Hermite-shaped functions. Tapi kalau kamu interested, kamu boleh tengok dalam dia ni dalam matematik je ni. Interpolation punya function. Kita ada Lagrangians, shape function pun ada. Hermite-shaped function. So boleh tengok kalau kamu interested. Alright, now we comes to the field displacement. Okay, field displacement ataupun in this notes dia panggil displacement function to determine deformation at any point on a beam within the two its nodal points. Macam yang kita pernah buat sebelum ni pun, kita ada beam structure, kita ada bar structures dulu. Then we have calculate the displacement dekat sini. Dan kita dah calculate Q2. Then tapi ini adalah displacement pada point. Tapi apa yang berlaku dekat sini? Kan kita nak tahu juga kan. Dan kita panggil dia UX. So similarly, for the beam problem, kita pun boleh buat benda yang sama untuk tentukan apakah yang berlaku kepada beam kita ni di antara dua nodes. Then the way we do this is by using interpolation saja. So dia macam gini lah, macam graf ni. Kita ada kita dah predict graf kita macam gini kan. Dan kita tahu exactly point sini berapa, point sini berapa. And then kita nak tahu dekat tengah-tengah ni. So sini kita tahu X dengan Y dia kita tahu. So kalau nak tahu yang Y ni berapa kat sini, then kita, let's say kita nak pilih position X dekat sini. Then kita just buat interpolation kan. Dan sama juga dengan finite elements. Actually the same things applied to the finite element. So in this case, kalau kamu dah ada graph, kamu boleh project aja, project the line, then roughly dah dapat dia punya value kan. Tapi value dia tu may have some small errors sebab kita pakai grafik punya ni je kan. Then to obtain a much more accurate prediction of the field displacement for the bar, then we can use this equation. Actually equation ni macam ni kita pakai dulu juga, N1 Q1 plus N2 Q2. But for the beam structure, we have to consider the vertical displacement and also the rotation in our structure, which is kalau kita tengok kat sini, this two equation is actually refers to kalau saya lukis ni untuk bar yang hari tu. So untuk beam, kalau saya boleh lukiskan semula, kita ada V1 and V prime 1. V prime 1 at node number 1. Kita ada V2 untuk node number 2. Dan kita ada V prime 2. So the first two terms in this equation, which is actually refers to what is happening at node number 1 in term of dia punya vertical deflection dan juga dia punya yang ni adalah actually refers to the V prime lah dekat sini. Ini adalah V prime. dV over dz adalah V prime. But before we come to this equation, similar to the past two problem that we've seen in the previous chapters, we have first to calculate dulu berapa V1, V prime 1 ni. Dan baru kita boleh solvekan this displacement function. So the last two terms which is referred to what is happening at nodes 2, and the first two here is for nodes 1. And then we apply this sama macam kita solvekan beam structures. Then yang ni saya tak perlu discuss detail sebab proses dia dah sama je dengan beam. Tapi hopefully you all go in details lah, fahamkan dV over dz itu apa benda, and then we apply the change rule to get the equations, our equation later on. Yang asalnya kita tulis dia dalam Cartesian coordinate system, tapi kita sekarang nak bekerja dalam natural coordinate system. Okey, kat sini dekat bawah ni dia ada diberikan which is dv over dx adalah actually refer to v prime, which is the rotation. And then substituting the terms yang kita ada sebentar tadi tu into this field displacement equation for the beam. Then kita ada new terms dekat sini. Kat sini baru kita ada V1 dengan V prime 1. Tadi kita nampak dV over dz kan. Actually that dV over dz tu, then bila kita solvekan dia sikit, apply the change rule, then kita akan dapat the terms the V prime as what we have in this slide here. So now our equation is written as a functions of ni lah, V and also V prime. So yang ni pun sama juga, equation akan diberi, cuma nanti kita tengok contoh macam mana kita nak pakai dia. So saya tak nak panjang lebar kat sini, nanti boleh tengok dekat apa tu videos dalam YouTube. So sama juga dekat sini, we apply potential energy approach to solve beam structures. Then to solve for the element stiffness metric, untuk derivekan element stiffness metric, we use the internal strain energy equation in our potential energy equation. Dan bila kita bekerja dekat situ, yang ni kita tak pernah tanya dalam exam ataupun test for you to derive, but it's better to know how or where this element stiffness metric can be derived from. So now as you can see, kita punya K metric is very big ni dekat sini ni. Untuk satu elemen kita ada 4 unknown degree of freedom. So our K local will have the K metric of size 4 by 4. So bila kita solvekan this part here, then sorry, so when we solve this part here, then you will get finally untuk beam structures, the local element stiffness metric, which is given by this equation saja. So apa yang ada dalam kita punya equation schematic, again the geometric informations of our elements. Kita ada E, modulus of elasticity ataupun modulus Young, and then I, which is the moment of inertia, and also the length of our element. So this will be the constant for our K metric. So dalam this square metric, so we still have the geometric informations need to be included. So itu je. Sebab untuk beam, our beam is often solved for a perfectly horizontal beam ataupun dia in perfectly vertical directions of the beam. So dia tak ada influence by the angles dekat sini. So theta is not involved here. Theta not involved. But when we come to the frame later, which is we have several beams, we join them together to form certain shapes, then the angle we play is important roles again, macam kita buat pada plane trusses kan. So this is our K. K will be supplied as well, so tak perlu risau. And then, alright, saya rasa kita rehat dulu sekejap. Around 10 minit boleh? mungkin some of you nak minum air, nak breakfast ke, sempat untuk ni lah refresh sekejap. So we come back at 9:25, something like that lah. 9:25. Alright. Semua dah ada ke? Kau masih breakfast lagi? Alright, I think we start. I don't know whether all of you are with me or not because I can't see you. And it's not necessarily to open the video cam as well. Sometimes it will make the meeting a bit lagging kalau kita buka apa tu dia punya video kan. Yeah, hopefully you all stay with me. All right, now we have look at the how we can treat the loading, the three loops that we discussed just now, which is the first one is the distributed loads. So when distributed loads apply to our structures, then for finite element analysis, we have to treat this distributed load accordingly, which is the distributed load that apply to our structures. We have to convert it into what we call it as an equivalent nodal force and moment in this case. So kita convertkan dia ataupun transformkan dia kepada equivalent concentrated force dengan moment. So so the detailed explanations of this what is happening in the equation you can see or you can view from my YouTube's videos on the YouTube, which is later on if we can imagine actually this equation should be read together with this the figure at the bottom here. So okay, tak apa. I just make it try to make it simple explanation dekat sini. Then kita tengok detail dia dekat bawah. So first, let's we imagine. So this is our beam structures. So this is our beam structures, which is under the distributed load. So the whole structure is exposed to the uniform distributed load, which is given by P kan, in this case. And then we know that the length of our element, which is given by LE. Other than that, other factor that we know the cross-sectional area, kita tahu the modulus of elasticity, that we know the moment of inertia of these elements. So from this, finite element cannot solve as it is, but somehow this distributed load must be transferred into what we call it as the equivalence nodal force and moment, which is bila kita transferkan dia from the distributed load, then we will transfer it into the equivalence nodal force. So arah dia ke atas kita punya distributed load, then we get the positive the similar direction for the force. And then at each nodal point, it will have the rotation or slope as well. So the way we write this the equivalent of the force and moments, which is we write it according to the positive sign convention tadi tu. Okay, positive vertical dengan positif in anti-clockwise direction. Tapi betul ke dia jadi macam ni kalau kita punya beam elements under this kind of distributed load, kan? Betul ke dia akan jadi macam gini? So let's look at this the next slide. Mula-mula kita kena faham tu secara fizikal dia apa yang berlaku pada kita punya structure. Dan baru kita boleh convertkan dia kepada equivalence nodal point dengan concentrated point dengan concentrated moments. So let's say our structures, kalau saya boleh lukis dekat tepi lah. Okay, we take this place. So let's say this is my beam. And then the whole of this beam, dia macam kita tarik the whole beam ni ke atas kan. So we supply pressure or we supply the distributed forces along this beam. So agak-agak ke mana beam ni akan deform? Let's say kalau kita fixkan dia dekat ujung dua ni kan. So ke mana arah beam tu? So dia akan deform in this direction, right? Saya guna yang color line, tak nampak kuning. So the beam will deform in this direction. So you can imagine kalau kamu ambil pembaris lah kan, you apply the moment pada kedua-dua ujung kamu punya pembaris yang lembik tu kan. So bahagian tengah dia akan melentur ke atas. Maximum point occurs somewhere at the midpoint of your rulers kan. So that's actually representing similar cases where the rulers is subjected to a uniform distributed load in upward direction. And this actually very similar to bila dia melentur ke atas tu, dia macam kita pusingkan dia kan, macam kita pusingkan dia kedua-dua arah. Kalau kita hanya tengok dalam apa ni, dia punya moment saja. Kalau kita tengok pada dia punya moment saja. So this moment we transfer to the second figures. Ini physically. So under this distributed load, our structures or beam structure will deform as represented by the green line here. And then if we consider the outward direction ni, kalau kita releasekan kita punya apa ni, the 2 point here, actually this point here have the has a freedom to move in the upward direction juga kan. So this 2 point here has the degrees of freedom to move in the upward direction. So physically, ini adalah arah moment dengan arah daya, the equivalent. Okay. Tapi kenapa kita lukis tadi semua dalam arah lawan jam? Kan? So when we apply the positive deflection and also the positive rotation, Then kita kena tengok all these forces kat sini ni. Which is the conversion dia daripada P. Okay, daripada P dia akan jadi PL over 2 untuk vertical displacement. PL over 2. Ini dia punya value dia lah. Okay. So dia punya conversion dia tu nanti you all baca sendirilah dekat sini. Okay, macam mana dia convertkan ni? Daripada point load, daripada distributed load kepada equivalence force and moment. Okay, saya just apa ni? Explain lebih dekat sini. PL over 2. And then untuk moment, dia punya equivalence moment berlaku pada loads adalah PL square over 12. PL square over 12. So ini adalah the physical condition yang berlaku. Okay, the physical, and then kita transferkan dia kepada nodal point and moment. But now we have to match from this apa yang kita ada on the figures ni, we have to match with the pada elements punya sign convention. So from there, kita dapati kalau saya boleh lukis another structures, elemen yang sama, okay. Which is kalau kita tengok all the vertical force, the equivalent vertical force is in the same direction of this sign convention. So kita happy, so kita tak perlu buat apa-apa. So we have the equation will follow the same as what we have in the second figure. So kita apply je PL over 2, then PL over 2 dekat sini juga. PL over 2. Okay, untuk moment, the moments from the physical kita transferkan dia kepada equivalent. Then kita dapati on this point, the moment is which is given by PL over 2 juga, PL square over 12. And the direction of moments pada node on the left hand side of our element, which is in the same direction as the sign convention. So kita happy. So kita nak letak plus pun boleh. Tapi, alright, if we look at this one, sebab physically, our structure should be bending like this, right? Sebab kita apply distributed loads in the upward direction, our structure will bending this way. Kamu ambil lah, kamu apply lah apa-apa kan. Kau nak letak pembaris, lepas tu kamu nak apply tekanan daripada kamu punya tangan ke apa, tapak tangan tu, tengok arah mana dia pergi kan. So it will bend in the directions of this, follow dia punya directions of the apa tu, distributed load tu. Tapi the moment, okay, dia dalam arah yang berlawanan. Tapi to make it consistent with the sign convention, then we have to follow the sign convention. So instead of kita ada apa tu, physically the moment in the clockwise direction, but after we convert it into the positive sign conventions in finite element, then our equation here will change. So dia akan jadi PL square over 12. Magnitude dia sama, cuma dia punya direction dah berubah. So dia akan jadi negatif dekat situ. So dalam susunan kita punya force, equivalent force and moment dalam kita punya apa ni untuk distributed load ni, then kita akan ada seperti sebutan dalam slide ni. Kita ada PL square square PL over 2 and PL square over 12. Ini adalah untuk node 1. Node 1 dalam saya punya gambar rajah ni lah. And then the pairs here, PL over 2 and negative PL square over 12. Ini adalah untuk nodes 2 in my slide dekat sini. So this is actually to explain to you where this minus came from. Okay, where this minus came from. So it came from the conversions of the distributed load into the equivalence nodal points and moments, which is physically dia akan berlaku macam gini. The moment should be in opposite direction between the 2 points. But later on, we have to adjust our figures here so that our force and moments to follow this finite element sign conventions. Positif ke atas dengan anti-clockwise positive. So that's why we have this one, which is actually will give you this apa ni? The vectors for the distributed loads. Tapi macam mana kalau distributed load tu ke bawah arah dia? Okay, kalau distributed load tu ke arah bawah, so the same thing apply. So now my distributed load is in the downward direction. So if you take a ruler, then you apply distributed load, you can press by using your hand. Then you can found that your structure will deform this way in the downward direction. So initially the black one, so it will different to that much. So in that case, the magnitude of the equivalent of the force and moment remain the same. Tapi now the force is in the opposite direction lah. Dia sama dengan distributed load dia. And then our structures, our beam bending in that way is likely we apply the moment in that direction kan. Kalau kamu ambil tangan kamu tu dua belah tu pusing dalam arah, satu dalam arah lawan jam, satu dalam arah jam kan. So your structure will bend that way. So similarly you can draw it here. Oh, dia akan jadi macam gini. So apa dia punya magnitude? Magnitude dia sama. PL over 2, PL over 2, which is P is your distributed load, L is the length of your beam element. Untuk moment, you still have the same PL square over 12, PL square over 12. So this is the progressions lah daripada physical. Kita nampak physical dia macam gini. Macam mana kita nak convertkan dia kepada equivalent force and moment. And then how can we convert it for the finite elements application. So this is from the physical, but we have to match it with our finite element models, which is the force should be in that direction, and then kita punya moment should be in that direction as well. So kita cuba matchkan di antara kedua ni. Then from there we found that dia punya force, equivalent force still the same in terms of its magnitude. But now in terms of the direction dia dah opposite. So kita bagi dia negative in this physically in the clockwise direction, tapi kita kena jadikan dia sama dengan finite element. So we will have negative to the PL square over 12 on the left hand side. On the right hand side, the moments, which is yang ni dah sama dengan yang ni. So this is will remain the same. So only one positive value yang kita ada untuk kita punya the force and moment. So if your problem involve the distributed load in the downward direction, then your matrix, the vectors, instead of yang kamu ada tadi, okay, this is what you have for the problem where you distributed load in upward direction. Tapi kalau downward direction, then you will have your F, which is equals to negative PL over 2, negative PL square over 12. Then you have PL over 2, negative, and positive PL square over 12. So this is how we convert from the physical beam deformations from the physicals to the equivalent to its equivalent the force and moment. So yang ni kena faham. Ini you, all of you need to understand how it works. So saya share dekat kamu punya ni lah Telegram groups. So you have to be very careful with the use of equation. You have to understand how your beam is loaded. And then itu je, and then untuk concentrated loads and moment tu kita apply direct macam kita buat untuk beam dengan apa tu, sorry, untuk bar dengan plate trusses, which is the moment and concentrated and moments and concentrated loads tu dia akan apply kepada nodal point tu sendiri. Okay. So from the knowns deformation, after we solve the system of a linear equation in the form of KQ equal to F, kita dah solve dah ini KQ equal to F, then our Q here actually the deformation in the form of V dengan V prime tadi kan. Kalau kita nak pakai V dengan V prime lah. Kalau nak pakai Q, kita boleh pakai Q. So from this information, then we can use this information in order to determine the bending moment within our elements. So macam mana nak pakai? So we apply the bending moment equation as given by equation number 1, and then now as you can see we are working in the Cartesian. Then we convert our equation so that we can work in natural coordinate systems. Then we will have the expression for the bending moment, which is will be given by this equation. So you can imagine we have calculated the V and V prime, ataupun dalam this case dia pakai Q1, Q2, Q3 and Q4. So yang ni kita dah kira from the system of linear equation just now. Sekarang ni kita nak tentukan how much the bending moments within this element. Then we supply the Z information. Let's say kita nak dapatkan dekat midpoint where Z equal to 0 sebagai contoh. Then kita supply this information Z berapa, Q1 berapa, Q2 berapa, Q3 dan Q4 yang kita dah kira daripada system of linear equation tadi tu. Kalau tak nak pakai Q, kamu boleh pakai V dengan V prime, which is akan merujuk kepada benda yang sama je lah. Kalau pakai V, dia akan ada V1 dengan V prime 1. Kalau nak pakai V dekat sini, V dengan V prime 2. Actually, it's representing the same thing but using different variables lah in this case. Saya suggest kamu pakai yang V supaya senang kita nak tahu. Okey, ni adalah berlaku pada node 1. Yang ni berlaku pada node 2 kan. Kalau 1, 2, 3, 4 ni kita macam susah kita imagine. So kita kena fikir sekejap. 1, 2 ni dekat mana kan. Kalau pakai V, dia straight direct. Oh, ni berlaku pada node 1. Ni berlaku pada node 2. Alright, similar to the shear force. So we apply shear force equation, convert from Cartesian into natural coordinate system. Then untuk dapatkan shear force within our beam structure, then we apply this equation at the bottom here. So all equation will be supplied. We never ask student to derive this as well. Sebab beam itself pun banyak juga dia punya nak kena buat. So we never ask in the test or exam for you to derive these equations. Alright, there is one example in this lecture notes. I think I'm not going to explain this, but I hope you tried it yourself. Cuma in this case, maybe you can cut short your process macam yang kita buat sebelum ni kan. We discretize the element and then we look at the body conditions, and then at this stage, at the local stage ni, so kita tengok kat sini, saya kecilkan dulu. If we look at the our problem at nodes number 1 ni, dia dah clamp dekat situ ni. So we know that at this particular point, so there will be no vertical displacement and there will be no rotation at this particular point. So V1 and V1 prime dekat situ, saya tulis kat bawah ni lah, V1 and V1 prime, we can eliminate it straight away. Dekat nodes number 2, you have to draw something like this for all nodal points. Then start to evaluate the body condition. Untuk nodes number 2, it allows the structures here to move left and right, tapi dia tak ada freedom to move in the vertical direction. And kita ada apa kat sini, V2 prime. So V2 prime. V2 also can be eliminated. So kita mungkin ada rotation sebab dia ada kita pakai pin kan. Pin, as I mentioned earlier, it allow your structure to rotate. Kalau kita ada vertical structure macam tu, kalau kita structure kita in the horizontal pun sama. It allow your structure to rotate to the left or to the right. So this is the how the pin behave lah. Pin support behave. So we only have one element in K1 to fill up. Untuk K2, kita ada 2 elemen sahaja. So you do not need to write everything. So saya tulis dekat tepi sini, we have V2 prime, V3 prime. So V2 prime. So V2 dengan V3 can be eliminated. So yang aktif adalah this 4 only. But ni yang prime dia dekat sini. So V2 prime exists in K1 and also in K2. So yang ni kita kena combinekan dia. Kita kena combinekan dia. So your matrix instead of kamu ada 1, 2, 3, 4, 5, 6 because you have 6 degrees of freedom dekat sini. Tapi tak semua aktif, 4 yang tak aktif. So you only have yang aktif adalah V2 prime. V2 prime. Dari V2 prime. Dengan V3 prime. So yang lain semua tak aktif. So kamu boleh eliminate sebenarnya semua ni. So yang hanya letter adalah this and this and this. Dengan dia punya depan dia tu jangan tertinggal lah. So if you have this, actually, okay. Actually kalau kita solve body condition, actually you can cut short. Tak perlu sediakan yang ni pun. Ni yang ni tak perlu sediakan. You can straight away go there. So there a lot of process yang kamu reduce tau. Okay, then you have to check for the force lah. Force ni you have to solve one by one and then eliminate yang mana tak nak pakai. So kita just supply apa yang kita nak pakai je. Then from this stage, starting from bar structures, you can plug in this number into your calculator. So solve boleh pakai calculator. Macam mana nak guna calculator, itu you have to learn lah. Calculator. So calculator. So in your calculator, you can input up to 3 unknowns. So and for that case, our test exam we limit the number of unknown up to maximum 3 unknowns. Kalau kamu solve kamu punya problem, kamu tiba-tiba dapati sampai 4 unknowns. Then you may have set your body conditions wrongly lah. Tapi itu starting from beam. Untuk the previous two, you have to solve it because we would like to test you the fundamental. Then you may have more than 3 lah. You may have more than 3. Sebab yang awal-awal tu dia tak ada melibatkan penggunaan calculator at all. So you have to be careful lah. Okay, I hope you try this yourself.